Welcome for the session. In this session, we are going to cover the frequency domain analysis. The next module. So in your syllabus, it is a module 4, frequency response analysis. In the previous module, we have solved time domain analysis or time response analysis. There are several signals in time response analysis. We have tested for ramp input, we have tested for unit step input, also the parabolic input. So while deriving the parabolic input, the process was very lengthy. You have to solve the equation, you have to solve the differential equation, after that you have to apply Laplace transformation, then you will be writing the solutions. So that is a procedure what we are solving in time response analysis, and the method is accurate. Time response analysis method is accurate, and some of the transfer functions, when we solve a parabolic input, second order system, undamped, underdamped, overdamped and critically damped system, those systems, the equations are much lengthy and somewhat time consuming. Suppose if you consider a higher order more than second order system, then it is very difficult to interpret the solution. Since it is an accurate method, we can follow it, but for the higher order, we cannot follow the time response analysis. In controlled engineering, there are two things. One is time and another one is frequency. What is the frequency? It is a reciprocal of time period. The next part what we will be doing is frequency response analysis or frequency domain analysis. Whenever we talk about response of the system, the response of the systems can be written in two ways. One is steady state response and other one is transient response. So initially the control systems will be like this. The amplitude will be high. We want high force, high torque or high amplitude initially because to overcome the inertia forces. After that it should be stable. So this is the characteristic of any good control system. So this control system will be having very good stability. Initially I need to have a higher amplitude. After that the amplitude should goes on decreasing and it will be zero. Practically what happens is initially the amplitude will be high, after that it will be like this. So it will be decrement in logarithmic fashion or exponentially the curve goes on decreases. So this is what we have seen in underdamped vibration. After that I want a stable output. I don't want any pulsating output. If there is any pulsating output, the system will have some disturbance. Because of this, error will be generated and output will be deviated. We don't want this characteristic. We don't want this oscillating one. We want stable one. But initially, we won't get stable one. After some interval, we will be getting the stable one by reducing the amplitude value to 0. This is what you have seen in logarithmic decrement. And the first part, this is a steady state part. Then after that, decreasing the value of amplitude. This decreasing is because of some damping. Since you are giving some damping to the system, the value of amplitude goes on reduces and finally it will be decayed and the system becomes stable. This is a response of the system. In the previous classes, in the module 3, you have solved what is a steady state response, what is a transient state response. There are several parameters. You have solved steady state error for the displacement, for the velocity and for the acceleration. You have derived an expression and that derivation is somewhat lengthy. Here in frequency response analysis, we will be analyzing a test signal. So suppose I will consider a system. This system is a linear system having an input of this frequency response is a sinusoidal. Say for example I will take A sin omega t and For this there will be an output. That output will be having b sine omega t plus phi. So the input test signal is sinusoidal, the output is also a sinusoidal in nature, but only the difference is, what is the difference here? Instead of A, the magnitude will be B. I need to know what exactly is that. So I will be calculate B by A. B by A is amplitude ratio. Amplitude ratio. Then phi. Phi is phase difference. In other words, what we can say is, we will be calculating what is the magnitude and phase angle for the plot. And the response of the system is calculated based on frequency domain. So, whenever the problem they have given in frequency response analysis, the first thing is you have to obtain frequency response function. Let us see what is the frequency response function and all. So before that, the input what we are assuming is A sin omega t, which is a sinusoidal. Output is also a sinusoidal, but the only difference is the magnitude as well as phase angle. If you locate the magnitude and phase angle, those values will be different for the output in comparison with input. So this is the thing we have to observe here. Let us write a curve, how it will be. Let us write a response, how this graph will be. So this is the input. Input is a sinusoidal which is having A sin omega t, but the output, there will be a shift here. This is also a sinusoidal. This shift, what we will call it as phase angle, and the magnitude, this magnitude is having A and this magnitude will be having B. This is what exactly the response curve of frequency response analysis looks. Let us see what are the advantages of frequency response analysis. Number one advantage is, whenever the transfer functions are complicated, it is very easy to solve here in frequency response analysis rather than time response analysis. The second thing is, here directly we are going to apply the sinusoidal test signals. Whenever the system is giving good response for sinusoidal test signal, it will give good response for rest of the signals. That is a very important thing is. That means if the system is stable for sinusoidal input, then it is stable for rest of the remaining types of test signals. That is very important. That means if the test is true for sinusoidal, it is true for all. That is the main thing, advantage in frequency response analysis. Let us try to locate what is the difference between time response and frequency response analysis. Sometimes time response analysis, it is also called as time domain. Frequency response analysis, it is also called as frequency domain, because the parameters what you are going to consider is basically a frequency parameters. That's why it is called frequency domain. Here we will be considering time domain specifications, time domain. So let us write this. The first one is, here in time response analysis, what we are going to get, the interpretation. The interpretation for the curve is direct. We will get direct interpretation. That means once if you calculate the second order curve, time domain specifications, you will get rise time, settling time, peak time, everything. By knowing into the time itself, you can say the system is stable or not. So that is a direct interpretation. Whereas in frequency response, it is indirect. How it is indirect? Basically, we will be calculating frequency, then 1 by frequency, we will get time. After that, we will be getting the interpretation. It is indirect approach. Then Second thing is time response analysis is accurate method. It is very accurate because analytical solution what you are getting is direct interpretation with the help of mathematics. But whereas here in frequency response analysis, here also there is a mathematical things involved in that, but the values what we will get is not so accurate since we are using a different plots like Nyquist plot, polar plot as well as Bode plot, logarithmic plot. Since we are using graphical interpretation, I won't say it is less accurate. Less accurate is an offensive word. I will be using it is approximate method. Here it is accurate method, here it is approximate. So instead of using less accurate, I have used approximate method here. Number 3. Here in time response analysis, here we have used a different parameters. What are those parameters? So that parameters will be called as performance parameters. Performance parameters. Here performance parameters are time domain specifications. Time domain specification. What are the time domain specifications? Here it is rise time, settling time, peak time. Also sometimes directly we will be calculating what is the natural frequency. So we have deduced what is the natural frequency of the system. Also damped frequency. So these are the important time domain specification. So these time domain specifications are the performance parameters in time response analysis. Whereas in frequency response analysis, we are using frequency domain specifications. These are the performance parameters. What are the frequency domain specifications here? Here it is gain margin, phase margin, then gain crossover frequency, then phase crossover frequency, then sometimes bandwidth is also important. So bandwidth, it is a range of frequency that also comes under frequency response analysis. So these are the different performance parameters we will be using in frequency response analysis, and sometimes this may ask in the examination for 2 marks, definition of gain margin, definition of phase margin, either definition of rise time, settling time, that will be also there. In module 3 you have studied this with a graph. Then after this there are several methods we will be using in time response analysis. One of the method is root locus, and another criteria is there, that is Routh-Horvitz criterion. So these two approaches are very important here, and the time response analysis is always based on location of poles and zeros. So that's why here we will be writing directly it is based on poles, zeros, location. That is another important here. So that location, there is a solution for that. That solution is obtained from Routh-Horvitz criterion. Based on the characteristic equation, we will be solving the characteristic equation based on the values and based on the location of zeros and poles. We will be telling whether the system is stable or not. Whereas here, in frequency response analysis, those are based on plots. So here, Nyquist plot, polar plot, logarithmic plot, or Bode plots. So these are the different plots we will be getting in frequency domain analysis. In another thing what you can write is, here it is based on pole zero location. Pole zero location, but Nyquist plot, it is based on Nyquist plot or frequency response analysis is based on encirclements about critical point -1 plus J0. At this point of time, it is very difficult to digest what exactly is this. After completion of module 4, I will be recalling again this, the differences, then you will be knowing what exactly these terms are. So this is the differences between time response analysis and frequency response analysis, or time domain versus frequency domain. Sometimes very important to know how to solve the transfer function using frequency response. Let us see. So what is the transfer function of frequency response? That is always there in the mind. What might be the transfer function? So in the time domain we have defined the same thing. Laplace transformation for output variable to Laplace transformation of input variable under the initial condition 0. Mathematical model we have done, block diagram algebra and signal flow graph, and even for time domain analysis also we have located the transfer function. Without knowing the transfer function, it is very difficult. The first thing is we need to know what is the transfer function. But how to derive an expression for transfer function for frequency response analysis? Here there is no such works. Very easy. Already I said, if the input signal is a sinusoidal, then the output signal is also a sinusoidal, but only the difference is the magnitude and phase angle. So B by A and phi will be changing. First, always I will consider a transfer function which is a closed loop transfer function, which is nothing but g of s divided by 1 plus g of s into h of s. I will solve a denominator part. If I solve denominator, 1 plus g of s h of s will be equal to 0. So this is nothing but it is a characteristic equation. 1 plus g of s h of s equal to 0. This specification we have seen in module 2 itself. If we solve this characteristic equation, then g of s h of s will be equal to -1. Oh, very simple. But you have to solve what exactly g of s h of s. So in the frequency response analysis, first we are going to solve this g of s h of s, which is an open loop transfer function, and that will be equated to encirclements about the critical point. So it is equal to -1. It should be equal to -1. What is this -1? -1 is just a number or a position of closed loop poles or zeros. So -1, if I write this in a complex form, it will be -1 plus j part, imaginary 0. That is a critical point what we will take. Let us talk about only the left hand side part, g of s h of s. Here g of s h of s is in the form of s plus 1 divided by s square into s plus 1 into s plus 2, like that. It is some function. So we need to solve it. How to solve? First you need to consider g of s h of s. After that, always replace s is equal to j omega. If you replace s is equal to j omega, then what happens? G of j omega into h of j omega. G of j omega into h of j omega. This is called as frequency response function. This is called as, very important, frequency response function. How did you got frequency response function? First, you have considered the open loop transfer function. In the module 4, in question, there should be an open loop transfer function always. Open loop transfer function, for that you have replaced S with j omega, then you got g of j omega into h of j omega. After this, find what is magnitude and what is phase angle. What is magnitude and what is phase angle? The transfer function will be in terms of magnitude and phase angle. This will be a transfer function for the frequency response analysis. Let us recall the basic things in calculating magnitude and phase angle for a complex number. So I will write that as a note. If I consider complex number, what is a complex number? A complex number is one which is having an imaginary part. So complex number x plus iy. What is the magnitude for this? Magnitude will be square root of real part square. This is a real part. It will be consisting of real part and an imaginary part. So real part I will be calling as real, imaginary I will call it as im. Instead of iy they can also call jy. So magnitude will be equal to square root of real part square, that is x square, plus imaginary part square, that is y square. What is the phase angle? Phase angle will be tan inverse of imaginary part divided by real part. For interpretation, directly I will write magnitude will be square root of real part square plus imaginary part square, and phase angle will be tan inverse of imaginary part by real part. Why we need to find out magnitude and phase angle? That itself is a solution or a transfer function for the given frequency response. That is very important here. So like this, we will be calculating magnitude and phase angle. That will be always there in all the problems. You cannot eliminate that. Also, you remember the values. J is equal to square root of minus 1. J square is equal to square this. You will get minus 1. J cube will be equal to, J cube is J square into J. You will get minus 1 into J. It is minus J. And J to the power of 4 is plus 1. These results will be always important in solving the problem. Just I recalled. Let us summarize the introduction part in the frequency response analysis. Frequency is a reciprocal of time period. We will be calculating the response in terms of frequency, that is called as frequency response analysis. How? We assumed a sinusoidal input for the linear system. The output is also a sinusoidal, but the only change is magnitude and phase angle. We have to locate what is the magnitude ratio or amplitude ratio and then phase difference or a phase angle. So that too will give you what is the transfer function for the frequency response analysis. And also we correlated the differences in between time response and frequency response analysis. In the time response analysis, interpretation is direct, here it is indirect. In time response analysis, accurate method, it is approximate method since there is a graphical problems involved in that. Number 3 is performance parameter, here time domain specification. In frequency, it is a frequency domain specification. Then root locus, root Horvitz criterions are the methods for time response analysis. Here Nyquist plot, polar plot, Bode plot, those are the methods. Then it is based on pole zero location time response analysis, but frequency response analysis is based on encirclements about the critical point minus 1 plus j0. How to get a frequency response function? So first you consider the closed loop transfer function, then solve the characteristic equation to a 0. After solving the characteristic equation, you will get g of s into h of s equal to minus 1. What is this minus 1? Minus 1 plus j0. What is this? This is a critical point, what we will call that critical point. So we will equate the solution of g of s, h of s to a critical point. That will be a analysis for the frequency response. How to do that? First, I will consider the open loop transfer function g of s, h of s. For that, I will be replacing s is equal to j omega. If you replace s is equal to j omega, g of j omega into h of j omega, that means it is giving a different values of magnitude and phase angle for different values of omega. If you vary omega, magnitude also varies, phase angle also varies. That is the concept behind this. Then find the magnitude and phase angle. So magnitude and phase angle itself is a transfer function for the frequency response analysis. Since we solve many number of magnitude and phase angle, you have to recall what is the complex number magnitude and phase angle here. So magnitude for a complex number is square root of real part square plus imaginary part square, and phase angle for the complex number is tan inverse of imaginary part by real part. This correlation is very important, and this is about introduction to frequency response analysis. Let us see what are the different frequency domain specifications. So this is very important concept. If you understand this concept, then it is easy to solve the problems. What are the different frequency domain specifications here? Number one, it is gain margin, which is denoted by GM, then phase margin, PM, gain crossover frequency, so gain crossover frequency, it is denoted by omega G or GCF, then phase crossover frequency, so this is omega pi or omega P or PCF. So these are the different notations what we will be using for frequency domain specifications. And all these things are, it is a measure of relative stability. In control engineering, there are two aspects. One is absolute stability and another one is relative stability. Absolute stability is obtained whenever the location of poles is on left hand side of S plane. Left hand side of the S plane. This is absolute stability concept. What you have solved time response analysis is those things directly which is based on absolute stability concept. Here relative stability we will be considering. Relative stability is related to this location of closed loop stability or location of poles of left side of the S plane. Here, if the poles are located on the imaginary axis, what happens? If the poles are located on right hand side of the S plane, what happens? If the poles are located on imaginary axis and further, the system will be unstable. The system will be unstable, because of which what we will be doing is, in frequency response analysis, first we will be calculating whether there is any poles situated on imaginary axis or right hand side of the S plane. By looking that into consideration, we will be comparing that with a left hand side of the S plane, and we will be writing what is the stability. That's why it is a measure of relative stability, because we are doing other part. Similarly, in the mathematics, probability of A. Solving probability of A is a direct method. Here it is like time domain. In frequency response analysis, what we will be solving is the probability of A is calculated like 1 minus A bar. So directly getting this value, that will be a time domain, and indirectly getting the value 1 minus A bar. So we are seeing this part, imaginary axis, and further this part is what, which is that 1 minus A bar part, which is in frequency domain. That's why it is indirect method. So let us see, let us understand what is the different frequency domain specifications. Before that, a Swedish American electrical engineer named Harry Nyquist has given some of the plots and the concepts in order to analyze the stability using Nyquist plots or stability of frequency response analysis. So frequency response analysis is almost based on the Nyquist plot, one of the approach what he has given. Let us understand what exactly is this. Consider closed loop transfer function g of s divided by 1 plus g of s into h of s. So if you solve denominator 1 plus g of s h of s equal to 0, then g of s h of s will be equal to, this goes like this, minus 1. If I express minus 1 in complex form, it is minus 1 plus j0. Nyquist plot I will write. First I will write this in imaginary and real axis. This is sigma real axis and j omega, it is an imaginary axis. So the plane what we will be writing here is, we are using complex plane or j omega plane. Complex plane is denoted as S plane or j omega plane. For this, I will find what is the magnitude and phase angle. Before that, first I will locate the point minus 1 plus j0. Where is minus 1 plus j0? Real part is negative, so this is a positive. Negative means here. j0 means it is exactly on negative real axis. So somewhere here. This is minus 1. So if I solve magnitude for this, magnitude will be equal to square root of real part square plus imaginary part square. It will be square root of 1, it will be 1. Phase angle will be equal to tan inverse of imaginary part. What is the imaginary part? 0 divided by real part is minus 1. So tan inverse of minus 0. So what is tan inverse of minus 0? Yeah, 180 degree. Very good. You have to remember this. Very important thing. 180 degree. Sometimes what we will use is, we will be using this as minus 180 degree line also. For the reference sake, if I locate the quadrant 0, minus 90, minus 180, minus 270, minus 360. I have located quadrant in clockwise direction, the angles are negative. The same thing if I locate the quadrant in clockwise direction, 0, 90, 180, 270, 360. See the equality. Minus 180 degree is also equal to plus 180 degree. That's why in the problems, most of the cases in the Nyquist plot, the reference what we will take is, reference will be magnitude m is equal to 1 circle and minus 180 degree line. So these two are the references we will be considering for the analysis purpose. So same thing, I will take minus 180 degree only. This is a minus 180 degree line. This is a minus 180 degree line. And this is a magnitude 1. Sorry, critical point minus 1 plus j0. What is the magnitude here? Magnitude will be equal to 1. How to represent magnitude 1? If you measure on real axis, it will be 1. If you measure on imaginary axis, it will be 1. Here also 1, here also 1. So the magnitude m is equal to 1 means it is a magnitude m is equal to 1 is a circle here. It is a circle. So this is magnitude m is equal to 1 circle. Whenever, if the plot is approaching this, m is equal to 1 circle, after this, what will be the value? M is equal to 2, m is equal to 3. If you make m is equal to 2, m is equal to 3, what will be the value of this? This value is changing. Compulsorily, it will be on imaginary axis only. If it is on imaginary axis, the system tends to become unstable. Tends to become unstable, but it is not unstable. It is a marginal stability point. Imaginary axis is marginally stability point. In other words, m is equal to 1 means it is towards the edge of instability. It is at just stable or just unstable point. After that, the system becomes unstable. So this is magnitude m is equal to 1 circle. If I consider a plot, the plot inside this magnitude circle. So this is a plot inside the magnitude circle. What will be the magnitude of this plot? Obviously it will be lesser than this circle. So this plot is having m is less than 1 magnitude. Similarly, if I write another plot, sigma j omega minus sigma minus j omega. So this is critical point minus 1 plus j0. The magnitude is a circle and phase angle is minus 180 degree, and this is a plot. This plot is having magnitude greater than 1. Here this plot is touching minus 180 degree line. So this point is called as phase crossover point. 180 degree corresponds to phase angle, hence the point is called phase crossover point. Similarly, this plot is touching magnitude m is equal to 1 circle that is corresponding to gain, hence it is called as gain crossover point. Phase crossover point and gain crossover point. Here, for the analysis purposes, these two are very important, and this will be always there in all the problems. Whenever I got a phase crossover point and gain crossover point, then what I will be locating this magnitude. What is this? This itself is the magnitude of the given frequency response analysis. So I will call this as A. What is this gain margin? Gain margin. So it is a measure of relative stability. Let us see what is the definition of gain margin. Gain margin is margin. What I will do is, for this plot, I will add some amount of gain. For the A, I will add some amount of the gain so that the magnitude should be equal to 1. In other words, I will be making A as 1. How to make A as 1? Multiply by 1 by A. That itself is the gain margin. So, it is the additional gain required to make the system. What actually it is making? It is making m is equal to 1. M is equal to 1 is, it is either the system is neither stable nor unstable. So it is making the system just unstable. So this is important. Additional gain is important. So if I transform this, gain margin will be equal to 1 by A according to that. What is this A? A is magnitude of open loop transfer function. Importantly, magnitude of open loop transfer function at what frequency? Here at PCP, very important, at this point, otherwise it will be wrong. At PCP, phase crossover point. In other words, magnitude will be always expressed in terms of frequency, hence I will call it as PCF, which is phase crossover frequency. What is phase crossover frequency? Phase crossover frequency, PCF, is frequency at which the plot touches phase crossover point. Or in other words, frequency corresponds to phase crossover point is called as phase crossover frequency. So this is a definition of PCP and gain margin. Whenever we are defining gain margin, phase crossover frequency comes here. Very important thing. Again I will be repeating. It is additional gain required to make the system just unstable. How you are getting this reference? This reference you are getting using phase crossover point, very important thing. That's all. Then let us see what is phase margin. Phase margin, again it is also a measure of relative stability. It is measure of relative stability, and it is the very important thing. Phase angle you have to measure in terms of angle. For the angle you need to have some reference. What is the reference? I will join origin with gain crossover point so that I will get one point. I will get a line, that is for references. So what is this? What is this? What is this? And from this line to this line, this is angle of G of S, H of S. That means it is a phase angle. So phase angle is nothing but, so I need to add some of the angle. I need to add some lag in order to make the system just unstable. I have to add some lag, that means lag, system lag I need to add. That lag will be corresponding to phase lag. So what is the phase, So in order to get phase angle, I need to have some reference in order to measure the angle. What I will do is, I will join the origin to gain crossover point. That reference I will got. So from real axis to this angle is angle of G of S, H of S. That means it is angle of phase angle of open loop transfer function. So I need to add this amount of phase angle in order to make the system just unstable. If I add this, it will be minus 180 degree. So this is phase margin. In other words, what exactly is that is, I need to add some of the lag. It is beside minus 180 degree. It is behind minus 180 degree. So what I need to add is, I need to add some phase lag. So that's why it is the additional phase lag required to make the system just unstable. So this is phase lag. Let us calculate what is the phase margin. Phase margin will be equal to, I need to want phase margin. How to calculate phase margin? I know angle of open loop transfer function, and this line I need to know. What is this line? 180 degree, straight line. So phase margin will be equal to 180 degree plus angle of open loop transfer function. So this is phase margin. And again, where exactly you will get phase margin? You will be getting phase margin at gain crossover point, at GCF. This you are getting at GCF. What is GCF? Gain crossover frequency is frequency at which the plot touches magnitude m is equal to 1 circle. So that is the gain crossover frequency. Here these two things we defined, but we need to analyze what will be the gain margin and phase margin. How to analyze? Here I need to add some amount of gain. I need to add some amount of the gain. Can I add some amount of gain? Yes, it can be added. Hence, gain margin will be positive. I need to add phase lag. Yes, it is possible. Here, gain margin is also positive, phase margin is also positive. If both are positive, then the system is stable. If gain margin and phase margin are positive, the system is stable. If gain margin and phase margin, one of these things are negative, the system is unstable. Here I have written what here? This is phase crossover point. Where is gain crossover point? This is gain crossover point. I will join these two. And this is angle of G of S, H of S. This become positive. And here phase margin is above minus 180 degree line here. This is phase margin and gain margin becomes negative. So M greater than 1, gain margin will be negative, phase margin will be negative, the system is unstable. Very important. This is one of the analogy what we'll be doing in the problems. And mathematically let us analyze the gain margin and phase margin. Here 1 by A, magnitude of open loop transfer function. If I solve that M less than 1, you will get this as a positive 1 by something. If generally gain margin is expressed in decibels, it will be expressed in decibels or a factor. So if magnitude become negative, minus 20 log 10, it will be a negative gain margin. Next, phase margin, 180 plus angle of open loop transfer function. If it is lying above, then this term is 180 minus something, it will be negative. If gain margin and phase margin are positive, the system is stable. If gain margin and phase margin are negative, the system is unstable. Here you have to remember a small thing. What is that small thing is, magnitude circle is less than 1 and magnitude circle greater than 1. If the magnitude is less than 1, gain margin and phase margin are positive. In other words, if gain margin and phase margin are positive for the stable system is having magnitude less than 1. Again, unstable system is having magnitude greater than 1 and gain margin and phase margin are negative. This is the first thing you have to remember. M is less than 1. So I will write here, if M is less than 1, the system is stable. For the stable system, gain margin and phase margin are positive. This is first analogy. Next, if M is greater than 1, the system is unstable. Gain margin and phase margin are negative. Then if M is equal to 1, the system is just stable or just unstable, or sometimes we will use marginally stable. This is one analogy. Second analogy is very important. Second analogy is depends upon where is the critical point minus 1 plus J0. Minus 1 plus J0. Here minus 1 plus J0. Where is minus 1 plus J0 in stable system? In stable system, minus 1 plus J0 is located inside the magnitude circle 1. That means instead of using inside the magnitude circle, before the phase crossover point. So that is the one thing here I will be using. So here inside the magnitude circle M is equal to 1, instead of using that, minus 1 plus J0 critical point is located after the plot. So minus 1 plus J0 is located inside M is equal to 1 circle. Instead of that, I will not write M is equal to 1 circle, it will be after plot, after the plot. Next, second thing, m is greater than 1. In m is greater than 1, where is minus 1 plus j0? So this is a plot. Before the plot itself, there is a critical point. So minus 1 plus j0 is located outside m is equal to 1 circle, that is before the plot. And since we are engineers, we don't write inside and outside. Let us use straight terms. For understanding, it is okay, inside and outside. It is after the plot and before the plot. If m is less than 1, after the plot, m is greater than 1, minus 1 plus j0 is located before the plot. So these two things very essentially you have to solve, because 20 marks problem is based on this. One is m is less than 1, the system is stable, and critical point minus 1 plus j0 is located after the plot, this diagram. Similarly, when m is greater than 1, minus 1 plus j0 is located before the plot only. So this is about frequency domain specifications, and this is drawn in polar plot or and e to the power of j theta configurations. Polar plot is a plot of magnitude versus phase angle. Polar plot is a plot of magnitude of j omega versus phase angle of j omega. This is actually a polar plot. What you have drawn here, this is a polar plot. So let us plot this for various problems. If you solve some of the problems, you will be knowing how this plot will look like. The next concept is polar plot. Polar plot is a plot of magnitude of g of j omega, or simply we can say magnitude of open loop transfer function versus phase angle of open loop transfer function. So magnitude of open loop transfer function versus phase angle of open loop transfer function. Already we have seen the polar plot. This is sigma, this is j omega minus sigma minus j omega. So first I will locate critical point, minus 1 plus j0. This is a circle. Polar plot, this itself is a polar plot. Polar plot is a plot of magnitude of open loop transfer function versus phase angle of open loop transfer function, provided if you vary magnitude and phase angle from 0 to infinity. Here omega varied from 0 to infinity. This is a condition, you will get a plot, polar plot. Let us see what is the procedure to solve a polar plot. The first one is consider open loop transfer function. In the problem, you have to consider open loop transfer function. What is that? G of s into h of s. In the problem, they can mention closed loop transfer function, they can mention characteristic equation, anything they can mention, but you have to consider only open loop transfer function. If you see any closed loop transfer function or a characteristic function, then you replace or you substitute those, and finally you get what is open loop transfer function, then you solve. After solving that, you have to replace s with j omega. S is replaced with j omega. J omega is the polar coordinates. So because of that, you are getting the different values of magnitude and phase angle for different values of omega. After substituting j is equal to j omega, s is equal to j omega, what is the magnitude? Magnitude will be equal to, you have to calculate square root of real part square plus imaginary part square, and how many functions are there. Calculate magnitude of g of j omega, that is open loop transfer function, and phase angle of g of j omega. So what I will write is phase angle of w magnitude of W. After locating magnitude and phase angle for different values of omega ranging from 0 to infinity. After calculating this, that you draw polar plot. For this, you will be having 8 marks. Sometimes it might be asked or may not be asked. We cannot say what exactly the question paper will be like. So, this is a procedure, actual procedure. Sometimes there might be an extension part. You have to locate the magnitude and phase angle or magnitude and frequency at intersection point. After this, you need to check whether the plot is crossing imaginary axis or not. After this, you have to check for intersection point. If the plot is crossing on intersection point, you have to locate what is the intersection point. The plot may cross on imaginary axis, the plot may cross on real axis. So intersection point might be there on imaginary axis, intersection point might be there on real axis. Specifically speaking, in this example only, this plot is crossing on real axis. You have to locate what is this point, that is intersection point, intersection of plot on real axis. Here, intersection of plot on imaginary axis, intersection of plot on real axis. If the plot is crossing, then find out the intersection point using the condition. If the plot is on real axis, imaginary part is 0. If the plot is on imaginary axis, real part is 0. By equating this, you will get the values of omega p. Then after that, after getting this omega, find out what is the magnitude. So that will give you the magnitude of the plot. Specifically, I won't write omega p or omega g here, just I will write omega intersection. Because sometimes you might get in phase crossover point only, sometimes you might get in gain crossover point only, but if you get omega here, what is that? It is not neither phase crossover point nor gain crossover point. So that thing you have to remember. So this is the procedure of polar plot. Let us take problem number 1. We will solve. First problem I will take. Draw the polar plot for open loop transfer function g of s h of s 10 divided by s plus 1. Simple problem we will take. 10 divided by s plus 1, directly they have given open loop transfer function. First step is we need to consider open loop transfer function. So g of s h of s will be equal to 10 divided by s plus 1. After this replace or put s is equal to j omega. If you put s is equal to j omega, g of j omega, h of j omega. What is this g of j omega, h of j omega? Frequency response function. Very important thing. Frequency response function. So 10 divided by j omega plus 1. Second step over. What is the third step? Find out the magnitude. What is the magnitude? Here I will take numerator. Numerator is 10. I will express this numerator in a complex form. So 10 plus j0. What is the magnitude for this? Magnitude is square root of real part square plus imaginary part square. So 10 square plus 0 square is 10 square. Root and square get cancelled. It will be 10. So magnitude for numerator is 10. What is the magnitude for denominator? I will calculate j omega plus 1. What is the magnitude for this? Square root of real part square. What is the real part square? 1 square plus imaginary part square. What is imaginary part? J beside. So omega square. That will be equal to square root of omega square plus 1. Either you can write 1 plus omega square. Both the things are possible. So this is magnitude. Then phase angle. What is the phase angle? So same thing if I take 10 plus J0. What is the phase angle for this? 10 plus J0. Phase angle will be tan inverse of imaginary part. What is the imaginary part? 0 divided by real part. It is 10. 0 by anything is strictly positive 0. Tan inverse of positive 0 is 0. If you get tan inverse of minus 0, 180 degree, remember. So numerator 0 degree minus. Why minus? Because denominator I am transforming to numerator. So 1 by tan inverse x will be equal to minus tan inverse x. So this thing I am applying here. I will write the denominator j omega plus 1. What is the phase angle? Tan inverse of imaginary part by real. Which is the imaginary part? Omega divided by real part is 1. It will be tan inverse omega. If I take that to a numerator, it will be minus tan inverse omega. So phase angle will be, so specifically what I will write is, I will write in a specific fashion only. Tan inverse of omega 0 minus, if I take that to a numerator, tan inverse omega. So 0 minus tan inverse omega, it is minus tan inverse omega. This is 5. Let us locate what is the value of omega, what is the value of magnitude and phase angle for different values of omega. First, if I give omega is equal to 0, what is the magnitude? 10 divided by 0 plus 1, it will be 10. And what is the phase angle? Phase angle, if I give omega is equal to 0, tan inverse of 0 minus tan inverse 0, it is 0 only. Then, if I give omega is equal to 0.2, the magnitude value, if you solve in calculator, it will be 9.8. If you solve for phase angle, it is around minus 11.3 degree. Then go up to infinity, solve 0.5, 1, etc. Then 10. If I solve for 10, the magnitude will be equal to minus 0.995 and the phase angle will be equal to minus 84.5 degrees something. Okay, calculate what is the value. Then finally I want for infinity. If I substitute infinity here, anything by infinity is 0. What is the phase angle? Tan inverse of infinity. Tan inverse of infinity is 90 degree. Since it is minus 90 degree. So the graph is going from 0 to 90 degree. I will write the polar plot. This is sigma. This is j omega minus sigma minus j omega. This is g of j omega, h of j omega plane. We will be drawing in polar plot. First, I need to see what is the value of magnitude when omega is equal to 0. It is 10. Positive 10 means here. It can be here. It can be here. It can be here. Magnitude is a circle. Remember, it can be anywhere. Specifically, you have to look direction. What is the direction? Direction is 0 degree. When omega is equal to 0, what is the phase angle? So phase angle is 0 degree. Then positively the magnitude will be here only. This is magnitude. Omega is equal to 0. Magnitude will be equal to 10. So this is first point. What is the second point? Omega is equal to 0.2. Magnitude will be 9.8 and minus 11.3 degree. Where is minus 11.3? 0, minus 90, minus 180, minus 270, minus 360. So this is the first point. Minus 11 point something is here. And then I will go at extreme limit. It is 90, 0. Phase angle will be minus 90. So 0, minus 90. So it will be here. Magnitude will be equal to 0 when omega is equal to infinity. So this is a point. So if I plot, it will be like this. So this is a polar plot. Importantly, you have to mention the direction of the plot. What is the direction of the plot? It is in clockwise direction. How it is in clockwise direction? Let us check. What is the angle? Minus 90 degree extreme, and what is the angle at omega is equal to 0? It is 0. So you take difference, minus 90 minus 0, it will be minus 90. 90 degree is the direction, but since it is a minus, you have to consider that in clockwise direction. Quadrants, how will you take? 0, 90, 180. You are going in counterclockwise direction for positive angles. For positive angles, you are going in counterclockwise direction. For negative angles, you are going in clockwise direction. So this angle coverage is 90 degree. It should cover one quadrant, but the direction should be in clockwise. So this is a problem. We have done everything. Yes, that is a polar plot. This itself is polar plot. And this is not crossing any real axis or imaginary axis. This itself is solution. No need of showing the magnitude. Directly, you can draw this by knowing omega is equal to 0 and omega is equal to infinity. That's all. What we have done? First we have considered the open loop transfer function, then put s is equal to j omega, then magnitude and phase angle. We calculated magnitude and phase angle for different values of omega, then we draw the plot. Next problem onwards, I won't write this, direct steps I will write. Since it is a first problem, I have written all those steps. Thank you.